Okay, this second part of the cosmological kinematics. So we can talk about how Hubble's law follows from the cosmological principle. The proper distance from a co-moving emitter at x em to a co-moving receiver at x receive at Cosmo t, which means it's the length of the shortest path from emitter to receiver in the spatial surface of fixed time. Is given by the uh, this is a function of t is by the co-moving frame, which is independent time, multiplied the scale factor. Okay, so this the right hand side, this d is a fixed co-moving distance at t naught. Now, if we differentiate respect to the cosmic time, we get the proper relation. The relative velocity v is equal to uh, uh, differential respect to t, and that turned out to be the the rate of a dot over a times t. You simply notice that if I write this as a more transparent notation, a of t times a d of t equal to a of t times d naught, and you differentiate with t, uh, only a you differentiate, and then you divide by a and multiply by a, and you get the relation over here. Now, obviously, this relation saying the velocity is proportional to the separation with proportionality constant. So therefore, so that's Hubble's law. Okay, and the proportion constant, Hubble's constant, is a dot over a. Of course, all these are time dependent. Okay, Hubble constant means it's independent of separation and velocity, but it is still as a function of cosmic time. In particular, when take t equal to t naught, of course, a of t naught is 1, so therefore h naught, the Hubble constant at present era, is equal to a dot at present era. Remember we said the Robertson-Walker metric follows from imposition of the homogeneity and isotropy conditions, so we can conclude the Hubble's law follows automatically from the assumption of homogeneity and the isotropic space, as in cosmological principle. So the scale factor is a key in describing the time evolution of the universe. In fact, because it usually is monotonic, it can serve as a kind of cosmic clock. The question is how can we measure the scale factor A of t? That quantity that has the observed quantity that has the simplest relation to the scale factor is the redshift of a light signal. Remember, redshift, the redshift defined to be the change of frequency, percentage frequency change of wavelength, or if you write out this delta lambda as lambda received minus lambda emitted, so so it's a ratio to wavelength minus 1. The wavelength, in fact, any length is scale as a, so therefore the ratio of a lambda received over lambda emitted is equal to the scale factor at the received time uh, divided over the scale factor at the emitted time. And so, especially if you take the received time to be our present time, t naught, so therefore this a t naught is 1, so there's 1 over t emitted times. Just uh, plug this into here. It just 1 over the and move this over is 1 plus z. Okay, so therefore 1 plus the redshift is equal to 1 over the scale factor. And this, of course, z is a measurable quantity, and so immediately translate into a measure of scale factor. For example, at redshift z equal to 1, Okay, of course, present era the redshift of RB is 0, and if you go past and the redshift is 1, the universe was so z equal to 1. This the left hand side is 2, so a is equal to 1 over 2. So therefore, the universe is half as large at present time. In fact, the common practice in cosmology is refer instead of to the cosmic time of the era, is to its redshift. For instance, the photon decoupling time, which is the time when the cosmic microwave is generated, is when the universe become transparent to light, is said to occur at the redshift equal to uh, uh, at 1000, 1100, okay, etc. So here's an exercise. This somewhat useful, but also just mainly as an exercise of how to work with these quantities. So we're going to talk about the Hubble's plot. Remember, we're talking about Hubble expansion. Discovery of Hubble expansion will present a plot of the distance to the emitting source versus the measure, the redshift. Okay, so what is the distance being plotted? It's clear what redshift is being measured, but what is the distance being plotted? So if the source is some standard candle, which means is a source with no intrinsic luminosity, and the distance is deduced by observing what we the observed flux, and emitted flux is related to the emitted uh, luminosity divided by the area 4 pi d square. So therefore, this defines the distance. Okay, this and this distance, because measured through the uh, measurement of luminosity, is called luminosity distance. So there's a definition of the luminosity distance. And in fact, so the Hubble plot is the distance, which means the luminosity distance versus the redshift velocity. Okay. However, the simpler distance in theory is the proper distance. That is, the distance appears in the Hubble's law, for example. Now, in a static universe, the luminosity distance and the proper distance are the same. Uh, so really doesn't matter. But on the other hand, we're going to work out the case in the expanding universe. They're different. The question of in what way they're different, how they're related. We show that in the expanding universe, the flux, because the flux is proportional to the amount of energy per unit time per unit area, is reduced by 2 powers 1 plus z. Okay, from the static case. It is reduced because energy is reduced because the energy in the numerator goes like a frequency or goes like one of the wavelength, and the wavelength scales like the scale factor. So this the scale factor at present time is 1, and this is scale factor at emitting time. And from the relation we derived last slides, that's equal to 1 plus z. Okay, so therefore the emitted that the received energy is related to emitted energy uh, scaled down by a factor of 1 plus z, because the energy scales like wavelength in expanding universe, wavelength stretched out. Another factor is the lengthening of remember the flux is energy per unit time per unit area. Now per unit time, uh, the time actually is lengthening in the expanding universe because the wavelength is related to time. Okay? Remember, the wavelength is equal to c dt. So the lengthening of the wavelength implies the lengthening of the time interval, and the reduction, because lengthening interval in the denominator, so therefore it means the reduction of the flux by another power 1 plus z. It was 1 over dt not equal to 1 over dt emitted by, had to multiply 1 plus z. So therefore, the flux, which is related to luminosity this way, is reduced, is in the static case, but in an expanding case, it is reduced by 2 power 1 plus z squared. So therefore, this quantity has to be reduced uh, by 2 powers 1 plus z squared. So therefore, you compare the left-hand side and right-hand side, and it concludes that the luminosity distance relates to proper distance in expanding universe by this 1 plus z factor, okay, which we need later in a calculation. But anyway, also in Hubble's plot, the distance is the luminosity distance, and the velocity is measured in terms of the redshift. So here are the takeaways of lecture 22. Uh, the, the working hypothesis, which is not checked by observation, the cosmological principle means space is homogeneous isotropic. So there's no special privileged place in the universe, which is Copernicus principle generalized to cosmology. Particular convenient coordinates is coordinating form. Each cosmic fluid element carries its own synchronized clock and the position labels. The Cosmological Principle implies the Robertson-Walker metric, which is a block diagonal. Okay, so that the s squared is equal to minus c squared dt squared because of proper time, and the scale factor times this, and this part is a fixed uh, uh, fixed coordinates for a 3D space with constant curvature, which can be a flat universe, open and closed universe, k equal to. And the scale factor A directly related to redshift, which say 1 plus z equal to 1 over A. And the Hubble's law rises automatically in a universe obeying the cosmological principle. So next lecture, so far we already talked about kinematic cosmology. Next lecture, we'll be talking about the dynamics, the time evolution of the cosmology. Now, Einstein equation for homogeneous isotropic space is the same equation is called the Friedmann equation. And there's a simple relation between matter energy content and geometry, between the density parameter and the curvature at k, because you'll see from the Friedmann equation or the Einstein equation implies this such a relation. And also Friedmann equation turns out, even though we say it's Einstein equation, GR equation has simple Newtonian interpretations, of course, which make it easier for us to remember its significance. Okay, that's the end of